Hello? Hello? Okay, good. Audio's working. Okay, let's see how we're doing on the lab. Printf. There we go. All right, somebody started. Okay. It'll get to the point about around the time you're done. And when I say printf, you go, yeah! Anybody have any questions? Derek, let's see if you...
The last questions, are they asked like in order, so that way they kind of help you as you answer each one?
Would I do such a thing? Are they asked in an order that will help? So the questions on the lab, are they asked in an order that they will help you, guide you through things? Frankly, I can't even remember what I asked on the lab. What did I ask you? Anybody got the lab right up convenient?
My name, my favorite color.
Well, you can answer those ones if you want to. I'm feeling the creditometer maybe a little on the low side on that one. Didn't I ask you, didn't I tell you to do the two phases, figure out where what calls main? That one, and then tell me what printf does? Yeah, let me see it. Okay, so all these questions are designed to make you be thorough on this. So, at what address does the TS7200 at what address on the TS7200 does the TS7200 side of the loader load the received program? You should already know the answer to that one. What routine resides at that address? That's pretty easy to figure out. Where's the source code for that routine? What does the routine do? How does main eventually? What's the difference between the load address and the entry point? Is there anything resident at the load address? Why doesn't the bootloader jump to the load address instead of the entry point? What happens if the entry point and the load address are the same number? Does the loader program work properly? Why or why not? Yeah, so they are not necessarily intended to be a procession of questions. They're intended to just make you be thorough in how you address this issue. Okay? Brad.
What's the best way to see what are in the .o files, and that is important to look at?
Okay, so the question is, what's the best way to see what's in the .o files, and are they important to look at? If you really need to look inside a .o file, you already know how to do it, thanks to 3720 last semester, which you took. You can object dump the thing. I would recommend against that unless you really, really need to. This lab is designed not with the intent that you do an object dump on anything. But I mean, if you are really up late at night and just can't figure out how to go to sleep, well, go ahead, object dump a couple things and look at it. I would suggest that you use the cross version of the object dumper because the object files are going to be cross-compiled binary, so you'd have to use RML obj dump. But when you've got these object files, they've got to be built from something. What are they built from? They're built from source code. What kind of source code? Well, they'll either be .c files or .s files. Where do you get the .c or the .s files? Garrett, where do you get those files? NewLib 1.9-5780, which is on the website. It's been there it's on Blackboard. It's been there the whole semester. .s files are assembly code. So some files are written in hand-coded assembly. Some files are written in C. Most of the files in there are all C code, but you are going to have to look at some assembly files. Now, for those of you who are ridiculous overachievers, which I'm sure you all are, there is the occasional file that's mentioned in the map file that you don't have source code for it. So just be aware. There's source code for everything you need, but there are some things that aren't there. The reason why they're not there is because they're generated as part of the build process for building GCC. They are included as part of the GCC source code. but the connection between what source code in the source of GCC and what object file gets produced from it is not necessarily obvious unless you go through the process of building the cross-compiler. So you don't need to go through that process in order to understand what I'm talking about in the lab. Okay? Other questions? Derek.
Was there like a different printf code for the ARM, or is it like the same printf code that just runs in the ARM?
So yes, the question is there a different printf code for what runs on the ARM, or is there one printf code for everything? So that's the beauty of this newlib source code. This is a package that you can download and you can configure and compile for whatever processor that it supports natively. So if you get down into the architecture configuration portions or the architecture specific portions of the code down here, you'll see a whole bunch of different processors, ARM, Zilog, MIPS, x86, a whole bunch of different stuff. Most of the source code for printf and the rest of the C runtime library is common to all architectures. They've developed this package so that they've filtered out anything that has to be processor specific down to a set of folders that is designated as this is the stuff for particular processors. So you can compile this source code tree for x86. You can compile it for the ARM. You can compile it for a whole variety of processors, and you can compile it for a whole variety of operating systems. So yeah, the most of the printf source code is shared between platforms. Now there are
Couple different versions of the printf source code.
So you found a couple of different versions of the printf source code in the source ball in the source tarball I gave you.
Well, we found one in that new lab folder.
Uh-huh.
We found one in the stuff from lab 1. What do we get there?
Okay, so you found a version of the printf source code in the code that I gave you for lab 1.
Oh, like underscore ANSI.
Uh-huh.
We found two versions.
You found two versions of underscore ANSI where?
Like one was in the new lab folder and one was in the...
Okay, so did you find two versions of that header file in the source distribution I gave you? Or did you find one in the header files that come with a compiler, the cross compiler, and another one that's in the... Okay. So part of the C runtime library source code is it comes with a header file, like stdio.h is a header file that you have to pound include when you're building your program. You don't have to have the source code to the C runtime library in order to build a program. You have to have the object files and all the rest of the stuff that are the artifacts of building the C runtime library in order for you to build a program. But you don't have to have this newlib source code. The proof of that statement is the fact that you've already built programs without having to download that newlib source code. But whenever you run p.c from lab 1, you have to pound include stdio.h in that file. That header file has to be available for people who use it. So if you're going to build a cross-compiled program, your cross-compiler has to have that header file. It doesn't have to have the source file. It doesn't have to have printf.c or stdio.c. It has to have the object files in an archive, but it doesn't have to have the source files for them. Okay? So part of the build process when you compile the newlib source code or whatever runtime library source code you're building, part of the process of building that is creating a set of header files or extracting the right set of header files that are designated to be header files that should be available for users. So it copies all those header files and it takes libc.a and libm.a, the other artifacts of the build process, packages them all up and puts them into specific locations in the distribution of the compiler itself. So yeah, you're going to get two copies of header files. You'll have one that's part of your cross-compiler, one that's part of the source code. Whenever you build a program, it's going to reference the one that's part of the cross-compiler. But they should be the same thing that's in the newlib source code because the cross-compiler was built with this source code that I'm giving you. Other questions? Good stuff. We're all content? Eager to go on, learn more about source code? Okay. So, onward and upward. We're going to blast through the programming and the small stuff. there's a lot of topics that are covered in the book on programming in the small that I'm not addressing in class. The reason why is because there are some, double screensaver on that one. There are some topics that I want to tell you about that I need to pound out straight so that you understand how C works. There's a lot of topics in the book that I'm not talking about in lecture that I want you to pick up on, that I want you to read about. So I'm talking mostly about C. I want you to read up on what's going on with Java and Ada and Occam 2 in the book, but by leveraging what you already know about C. So the book gives you a presentation about, here's what this looks like in C, here's what this looks like in Ada, here's what this looks like in Java, here's what this looks like in Occam. And then it goes through different types of things, like declaring structures, declaring data types, how you do math, and so forth. So read through that stuff and be aware of it. I am going to give you a brief homework assignment on some stuff that's found in Chapter 3. Brief. Labs are not brief. Homework assignments are intended to be like an hour long or no more. Okay? So as soon as we get through this stuff, I'll give you that. Okay. So, remember last time we started talking about what is a char, and I showed you this printf code where I said, okay, you got a char, A and B, you do this math on it, and you say printf %C, and we said, what does this print? And we agreed that that prints the value 2, which is some nonsense ASCII number, STX, because %C says interpret whatever you've got as an ASCII character. So it takes the 8-bit integer and looks up the ASCII equivalent of that 8-bit integer and then prints the result. So a char then is a signed 1-byte integer. Okay. Let me ask you this much. We've talked about this one before. What is a pointer? Okay. So I've asked this one a few times, and hopefully I'm going to beat it into your heads a few more times. What is a pointer? A pointer is a variable. Okay? Just like a char is a variable, just like an int is a variable. A pointer is a variable. What is a variable? The memory location. Okay? How big is an address? On a 32-bit machine, you have a 32-bit address. Okay? 32-bit machine does not mean your int is 32 bits. It means that your address of all your values are 32 bits. Okay. A pointer is a memory location. It has an address. It contains an address. Are those two statements redundant? Could they be? Can you design me a statement of C code where you can say, here's a pointer, it contains an address, that is its address? That'd be funky. Why would you want to do that? Because I put it on exam, that's why you'd want to do it. Okay, usually what you're doing is something like this. Int A equals 5. Int star P equals address of A. So we've got, is A a pointer? Is A an address? You're saying A is an address, or A, what is A? A is a variable. What is a variable? A memory location. Is a memory location an address, or does a memory location have an address? A memory location has an address. The symbol A is an alias to that address, or to that memory location. Okay? Is P an address? What is P? It is a variable. What is A? It is a variable. What is a variable? It's a memory location. A memory location has an address. It is not an address. It is an alias for an address. It's similar to an address, but it is not an address. A pointer variable contains an address. Stupid, lousy semantics. Okay. Diagrammatically, it looks like this. We've got the pointer P, which is a memory location that contains bits. That bits happen to be, we interpret that as an address. In this case, because we've assigned P the address of A, what we've done is we've written to the memory location indicated by P the bits representing the address of the memory location A. Okay? So in each memory location, we represent as a little box. If it's a pointer, we use an arrow starting at one box, pointing to another box to indicate this box contains that box's address. So by saying int A equals 5, we put a 5 inside A's box. Saying P equals address of A, instead of writing down the address of A inside the P box, we just say that we draw an arrow from P up to A's box saying P points to A. What does this look like actually in memory? So suppose we've got these two variables that are allocated in memory, A and P. We're drawing here, memory is just a big 4-byte array. You can draw it as a 1-byte array. Here we're drawing it as a 4-byte array. Okay, so A represents this slot. It's 4 bytes because we're working on a 32-bit machine with a word size of 32 bits. Okay, and so P is also 4 bytes because it is a pointer variable and it takes up 4 bytes. Every address is 4 bytes. Okay, so let's suppose that A resides at the address 0xabc0. And let's suppose that P resides at the address 0xabc8. By assigning to P the address of A, what we do is we write into this memory location, indicated by P, the value of A's address. So P in this box gets 0xabc0. Okay? This is what goes on physically in the machine, this stuff that's in memory. This is how you think about it. Okay? What this arrow means is that this P memory location contains the address of that other variable. Yeah.
Maybe this is a simple answer, but why, with all pointers, like all pointers have the same file for the same size, that's the 32-bit machine with these 4 bytes. Why do you have to declare the data type for the pointer?
Okay, that's an excellent question. So the question is, if all pointers are of the same size, why do we have to associate a data type with them? Why do we have to distinguish between pointer to integer and pointer to char and pointer to this and that? Let me answer it in just a second in the context of a void pointer. Okay. A pointer points to an address on a byte addressable machine. So x86 are byte addressable machines. What that means is every byte in memory has a unique address. Okay? So how many addresses does A cover? When we declare int A, how many address locations is that? How many bytes is that? 4 bytes. How many addresses does that cover? 4 bytes. Byte addressable machine. Every byte gets its own address. So there are 4 addresses associated with the 4 bytes covered by int A. When we say that P gets address of A, does that mean we've now declared an array of 4 addresses, and that array then somehow gets associated with P? So if you take an address of an int, and you say, I want to know what the address of that int is, which one of the 4 addresses is it? Or is it all 4? Garrett.
That's why we declare the type that knows how many bytes to read, because the address we get is going to be a star address of space with an integer. It's going to point to the first location for that integer, so that is just 3, 4 bytes for character 1 byte.
Okay, so let me try to unravel all that. You are right. Yeah, absolutely. That's all right. Let me try to unravel all that. So, yes, that is effectively the answer to what you were saying. That we have the need to know how many bytes is covered by the object that we're pointing to. What you said implicitly is that every memory location may have multiple addresses associated with it, or every multi-byte memory location has multiple addresses associated with it. But you said that when we take the address of an object, it's the base address of that object. What do we mean by base address? So if you've got 4 bytes, and we up here said A is at the address 0xabc0. Well, is it really at that address? What address is that of? The A covers 4 bytes. First byte. What do you mean first? Least significant, most significant? Does it cover the addresses 0xabc0, 1, 2, and 3? Or does it cover ABB Let's see if I can subtract there. So F, E, D, and C. Where are the other three addresses, are they higher, bigger numbers than this or lower numbers than this? Bigger numbers. Okay. So if we consider this as an array of 1-byte numbers, this is C0, C1, C2, C3. Okay, 1, 2, 3, 4. All of that is A. Okay? So APC0 is a pointer to the first byte in the sense that we consider this to be a 4-byte array, and the subsequent bytes come after it in linear order in memory. Okay? So ABC0, ABC1, ABC2, ABC3. Likewise with P, you'd have ABC8, ABC9, ABCA, ABCB would be the addresses associated with that pointer. But when I take the address of a multi-byte variable, I just get the bottom address. I just get the address of the lowest number address. Okay. What's stored at that address? Least significant byte or most significant byte? Depends on... Does it depend on your operating system? Does it depend on your compiler? Does it depend on what you ate for lunch? Okay. All right, so here, if we've got an int I equals 3, we've got a multi-byte location here. Char C equals 3, covers one memory location. C is associated with this one memory location. Its address is beef, so we can put the 3 right there in that one address location. If you have a multi-byte location where you say I equals 3, that is 4 bytes, 3 bytes are zeros, 1 byte is 3. So when you look at this in a register, you see this right here, 0003, if you chop that up into bytes. You have the most significant byte and the least significant byte. So now the question is, when we store that in memory, which end goes where? Okay. There are 2 different ways of specifying which byte goes where, and it's called the endianness of your machine. You can be either big endian or little endian. Okay? Big endian, the most significant byte goes at the lowest address. Little endian, the least significant byte goes at the lowest address. So the endianness says, who goes at the lowest address? Big N first or little n first? Okay. Is your x86 big endian or little endian? Little endian. Okay. How about your ARM? Little. And that's good. How about a MIPS? MIPS is big. How about PowerPC? Big endian. Okay. How about a PlayStation? Cell processor. It's just a PowerPC, so it's big. All right. So let's suppose we have int var equals 0x1a 2b 3c 4d, and we've got a big endian machine and a little endian machine. Here's how they get represented. So on a little endian machine, you'd see 4d written here at the lowest address, followed by 3c 2b 1a. On a big endian machine, it's 1a 2b 3c 4d. Okay. Do you always have to remember whether or not you're working on a big endian machine or a little endian machine? You typically don't have to care. And that's a good thing. Why? Because when you take an int, when you declare an int and you set a value to it and you write it out to memory, your hardware will take care of ordering the bytes into RAM in the right order. And if you read that int out as a 4-byte int, your hardware will take care of ordering the bytes as it brings them into the machine appropriately. Where you get into trouble is if you go from a big endian machine to a little endian machine, or alternatively, if you say, I want to write out a 4-byte int, but I want to read it in as 1 byte, as a sequence of 1 byte. Okay? So you can consider an int as a 4-byte char array. You can do that if you want to. In fact, it's even more efficient if you write it out as an int instead of as 4 individual chars. So, but you get yourself into trouble when you write out a number as an int, but you read it back as 4 chars. So that way you need to pay attention to which byte gets stored where. Okay. Here's a question for you. Can you write a C function to determine the endianness of a machine? I would suggest being able to do that. Okay. All right, so this is all. You don't need to worry about this usually, but when you read a byte and write as a byte, then it gets into trouble. Okay, so here's an example of how you can get into trouble. So let's suppose you have that integer variable var, which is 1a, 2b, 3c, 4d, and you say int star I pointer equals the address of var. And you say char star c pointer equals the address of var casted to be a char star. Okay, what number does the memory location, first off, how big is the memory location indicated by I pointer? What is I pointer? I pointer is a variable. It is a pointer variable. Okay? It contains the address of another variable. We're not worried about the other guy yet. We're worried about just this guy. How many bytes does what size of I pointer? What size of C pointer? How many of y'all vote it's 1 byte? Oh, raise your hand. These two guys are both addresses. These two guys are both pointer variables. The size of them is indicative of the size of the machine, the number of bits of the address space. So both of those guys are 32-bit addresses. So after these two statements execute, let's suppose that the address of var is that beef. Okay? What does I pointer contain? Bad beef. What does C pointer contain? They contain the exact same number. What is this casting business doing? It does something, otherwise, if you don't use it, then the compiler is going to yell at you. So, does it tell what byte from the base to look at? Nope. It tells your compiler, trust me, I know what I'm doing. Don't yell at me. That's all that it does. It applies no conversion. There is no math done there. All it does is just tells the compiler, look, trust me. I got it. I'm here. I'm the man. I know what I'm doing. Okay. So what this does is, after these two statements execute, they both contain the same number. Now, what happens when you dereference these pointers? So if you say star I pointer, what are you going to fetch? Your compiler will emit an instruction that says load from a memory location contained in this particular register a particular number of bytes. How many bytes does it know to fetch? Depends on the type of what? I feel like that all the time. It must be Monday. Okay. I pointer is a pointer to an integer. Does it depend on what the pointer points to? In an ideal world, it should. What does the pointer point to? Right here. It points to var. How many bytes is var? 4. What does C pointer point to? What is it currently pointing to? So it's pointing to a 1-byte number or a 4-byte number? We pointed it to an array of 1-byte numbers. This is what this does. It says, well, you've got a memory location right there. I'm going to not think about that as a 4-byte number when I'm using C pointer. I'm going to think about it as a bunch of 1-byte numbers. This says I'm going to think about var as 4-byte numbers. There are two different ways of accessing this. They both contain the same number. When you dereference I pointer, you fetch 4 bytes. And that'll get you the value 1A, 2B, 3C, 4D. If you dereference C pointer, you fetch 1 byte. You get 0x4D. on a little Indian machine. Okay? The reason why is because the compiler can't figure out, the compiler is smart in a lot of things, but on this case, it's going to give up. Compilers give up when you deal with compilers give up when you're dealing with pointers and pointer dereferencing. The compiler's not going to figure out what is it that this thing points to. It's going to use what's the declared type of the pointer. And because the declared type of the pointer, CPTR is declared to be a pointer to a char. And so when I dereference a pointer to a char, that means I want 1 byte. IPTR is a pointer to an integer. So when I dereference a pointer to an integer, that means I want 4 bytes. Yet again, another example of how C lets you get away with murder. Okay. How does this work? When the compiler sees a dereference of an integer pointer, it will emit an assembly instruction that says fetch 4 bytes, ld.w. This is a variant of ARM assembly over here. Okay, star CPTR, ld.b. This says load a byte. R2 would be the register that contains the address that the pointer points to. So load from the address contained in R2, put the result in R3. ld.b says load from the address contained in R2, 1 byte, and put that into R3. Okay? Even though it's the same memory location, the declared type of the memory location that you pointed these pointers to is an int. And you initialized it with an int. You can access it as if it were a char or an int. Okay, now let's look at void pointers. Okay, what is a void pointer? This is how you pull the pants down on your compiler. Okay? When you want to not have a data type, you say, or when you don't know what the right data type is, okay, you use a void pointer. It just says this is an address. So this is what you were talking about. Why don't we just use void pointers? Okay, so we can say void star vptr equals address of var. Completely legal. However, when we attempt to dereference vptr, the compiler is going to say, you can't do that. Why can't you do that? Because I don't know whether to emit an instruction that says load a byte or load a word. All I know is I need to load something. How much should I load? I don't know. This doesn't say how big it is. And it explicitly doesn't say how big it is. You cannot dereference a void pointer. You can cast this to be a pointer to a char, or a pointer to an int, or a pointer to a float, or a pointer to a double, or a pointer to whatever you want, and then dereference it. But the compiler will not, it can't dereference, it can't emit an instruction for dereferencing a void pointer because we don't know how many bits are associated with it. So that's why you have to have a declared type for a pointer. Because when you dereference the pointer, you have to know how many bytes to fetch from memory. Okay? So a pointer is a variable, a pointer is a memory location. It is located at an address in memory just like any other variable. Pointers contain addresses. Now here is something that often will trip you up. How do you assign an address to a pointer? Well, you use the address operator, or use the equal operator, the assignment operator. Pretty straightforward. How do you get the address to assign to a pointer? Ampersand. This is address of. iPointer equals address of var. How do I access the memory location pointed to by a pointer? That's where you use dereferencing. Use the star. Star iPointer equals 3. This says I want to access the memory location pointed to by iPointer. When you're using it on the left side of an equals, that means I want to write to it. When you use it at the right side, that means I want to read from it. Can I determine the address of a pointer variable? Why not? A pointer is a variable. It has an address. It contains an address, but that's beside the point. So how can I figure out what that address of the pointer variable is? Well, if you want to figure out the address of any variable, you use the address of operator. Well, what's the data type of the address of a pointer? It's a pointer to a pointer. So int star star iPointer pointer equals address of iPointer. Now, then you can go through and say, under the assumption that you've already assigned iPointer equals the address of var, then you say iPointer pointer equals the address of iPointer. You can say star star iPointer pointer equals 3. And you can do it again. You can have an iPointer pointer pointer, star 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 equals ampersand ampersand, blah, 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 blah. You know, this can go on forever. Okay, now how about star char star iPointer pointer equals 3? So, under the supposition that iPointer pointer points to the address of iPointer and iPointer points to the address of var, you can dereference the iPointer pointer, which gets you the value of iPointer, pass that to be a pointer to a char, dereference that, and assign that resulting memory location the value 3. So what that'll do is it'll put a 3 at the bottom of the array of bytes. So now you have 3, 2B, 3C, 4D. One more? Okay. So you can do all kinds of funky stuff with pointers and casting, but you have to know what you're doing, and you have to pay attention to what you're doing, and you have to know how big things are. So be careful. Okay, garbage pointer. A garbage pointer is a pointer that's not initialized. A null pointer. A null pointer is a pointer that's initialized to 0. Null is a pound define that's defined, you ought to be able to find the definition of this thing, to 0. Okay, so null is 0. It's the same thing. It's just a pound define. Okay, what is a dangling reference? It's a pointer that used to point to something, but now it doesn't point to anything useful. So here's an example of dangling references. Let's suppose that I've got a pointer P and a pointer Q. So suppose that I say int star P equals malloc 5. So I'm allocating 5 bytes off the heap. And I say int star Q equals P. So this says I'm going to have this pointer Q and I'm going to point it to whatever P points to. So I've got 2 pointers that both point to the same memory location. Now suppose I go through and do some other shenanigans, and then finally I say free P. And then I say P equals null. So what that does is it gives this memory back to the heap. And I set P to null. Now what's Q pointing to? No. Still pointing to that thing I just gave back to the heap. Now let's suppose that you went through and said star Q equals 3. You're all of a sudden writing to memory you don't have access to anymore. Well, let's suppose that Q is a global variable, and instead of just doing this right after you set P equal to null, so let's say you set P equal to null, then you go do 100,000 other operations which involve a whole lot of heap allocation, and then later on you say star Q equals 3. Well, chances are this block that you gave back to the heap has now been allocated to somebody else. And let's suppose that that somebody else has a data structure that has the control operations for a particular anti-lock brake system. And now let's suppose you write a 3 into the middle of it. And all of a sudden that tells your anti-lock brake system, randomly apply brakes in the middle of the freeway. You know, these things, this dangling reference can be quite a dangerous thing because you can inadvertently write to a memory location that you shouldn't be writing to, but the code looks completely legal. It's just if you had 2 pointers pointing to the same memory location, but you used one of them to get rid of that memory location, the other one still thinks it's valid, but it's not. You write to that, you can get yourself into trouble. Okay. So be careful. There's 0 compiler support for detecting this. Okay? This is a common mistake, and there is no way to catch it. You have to catch it, Mr. Programmer. There is no compiler support to catch that guy. So be careful about dangling references. Okay. Variables are memory locations used to store data. Where in the memory is your variable stored? Well, that depends on how it was created. You can create things statically. You can create things dynamically. Okay. By static here, I am not talking about the keyword static. I'm talking about you can do dynamic allocation and you can do non-dynamic allocation. Okay. Dynamic allocation is heap allocation. This is when you're using new and delete in C++. Or malloc and free in C. Okay? Static allocation, these are the variables you declare by saying int var. Okay? You can also statically declare a pointer variable by saying int star ptr. You can say int star ptr equals malloc size of int. You have 2 variables there, the pointer variable and the variable it points to. The pointer variable is a static variable. The variable it points to is a dynamic variable. Okay? So here you have, these guys are static variables. You can use the pointer to point to a dynamic variable. When you have a dynamic variable, it is the variable that's allocated off of the heap, not the pointer. Okay? The pointer is typically a statically allocated variable, but it can be dynamic as well in the case of like a linked list. Okay, you have 2 types of declarations. You can have local and global. Local, those are variables that are declared within a block. So int var here within the block inside main. That's a local variable. They reside on the stack. Okay? So stack is a large pool of memory where you have temporary variables pushed on and popped off as necessary. But that variable is alive until the scope in which it's defined goes away. Okay? Sequential programs only have one stack. All right. When you enter a function, the first thing you do is you adjust the stack pointer by the number of bytes equal to the size of its stack frame. So when the compiler compiles your program, it's going to calculate how many local variables do you have, how much space do you need to hold all of that. One of the first assembly instructions that you don't see when you're writing a C program is an adjustment of the stack pointer. You will see that when you start looking at ARM assembly when we get into some later labs. Okay. Where are global variables held? They're held in global memory space, either in BSS or the data section. We've talked a little bit about that. Dynamic memory. Where are dynamic variables held? They're held in the heap. Okay, so scope and persistence. Local variables have scope and persistence limited by their declared block. What does scope mean? What's the scope of the variable? The range of statements over which it's valid to access a particular variable. What's the persistence of a variable? How annoying it is? So the persistence of the variable is how long does that variable live for? Okay, so scope and persistence of a local variable are both limited by the block. So the range of statements that have the ability to access in a valid way the particular variable that's a local variable is defined by those statements that are contained in the block in which the variable is defined. The variable persists as long as the statements, as long as the system's executing the statements in that block. So when the function returns, the stack pointer is adjusted to erase those variables that were allocated on the stack frame. So when you first start a function, you allocate space on the stack frame for your local variables. When you return, you erase that space by just deallocating or moving the stack pointer down. Okay. Global variables have global scope and persistence. So what that means is any statement anywhere in your program can access a global variable, and they persist for the lifetime of your program. They're around, they live while your program's running. You don't allocate them, you don't deallocate them. Okay. So here's a couple rules for global variables. You only declare a global variable once. Your compiler needs to see the global variable's declaration, and the compiler only compiles one file at a time. And remember this other thing is that when you have a variable, when the compiler sees an access to that variable, when you're going to read from a variable, you got to know how many bytes that variable is. So you got to know if you're going to fetch 1 byte or 4 bytes. So that's why the compiler needs to see a compile time declaration of what is the variable. Okay, so under this scenario here, file 1 and file 2, two C programs. I'm declaring a global variable in file 1.c, int gvar equals 10, then int main, and I call some function. Function is defined over here in file 2.c, where function accesses the global variable gvar and sets it equal to 3. Okay, look at this closely, and look at rules 1, 2, and 3. You can only declare a global variable once. The compiler needs to see the declaration. So when the compiler compiles this file, it sees the declaration. The compiler only compiles one file at a time. So when the compiler compiles file 1.c, life's good. When the compiler compiles file 2.c, are all the rules met? Can the compiler see the declaration of gvar? Cannot see the declaration of gvar. Okay? Why doesn't the compiler just sneak over to file 1.c and look at it over there while it's compiling file 2.c? Rule number 3 says you can only compile one file at a time. So why don't I just put a declaration, why don't I just copy this int gvar equals 10 and put that into file 2.c? I violate rule number 1. Okay, so global variables have global persistence and global scope, but how do I access a global variable in a file in which it was not declared? So you have to have some type of forward declaration mechanism. The same rule holds for functions. So the compiler, when it compiles the function call to fn here, it has to know what this function is. It has to know what parameters it takes. So file1.c had better contain a prototype, or #include a header file that contains a prototype to fn, so it knows how to compile and access this function that's defined elsewhere. We need to have some ability to have a prototype for a global variable. Okay, so the way you do that is you use the extern keyword, extern int gvar. That gives a forward declaration of gvar. What that says is, somewhere else there is a definition of a global variable named gvar, and it's an int. So this tells the compiler that there exists a variable somewhere, and it tells it what its data type is. But it does not tell it, please allocate space. Without the extern, it says, please allocate space. Okay, so the presence of that extern is very important. Okay, scope and persistence with dynamic memory. Okay. Dynamic memory, the heap itself persists over the lifetime of the program. However, the variables you allocate from the heap persist only between the time that you allocate them and the time that you delete them. So you use malloc or calloc to allocate, use free to delete. Okay, if you don't free, the memory that you've allocated will persist the lifetime of the program. Okay, so if you just simply allocate a heap allocated variable, you set a pointer equal to it, and then you set the pointer equal to null without calling free on the pointer, what that'll do is that'll be a memory leak. And so that memory that you've allocated from the heap will continue to persist. You won't be able to recover that and reuse it in this program in the future. So that's a bad thing. So you got to make sure that you manage your persistence of your dynamic memory. Scope is limited by the scope of the variable you use to access the dynamic variable. So this pointer variable is typically a statically allocated variable. The variable it points to is, in this case, would be a dynamic variable. So what is the persistence and scope of this guy? The scope of this guy is limited by the scope of that guy. The persistence of this guy, he persists until you give him up, until you free him. Okay? So you've got to be careful with both scope and persistence. The problem is when you lose track of persistence of a heap allocated variable, then you get in trouble with a memory leak. When you lose track of scope, you end up with dangling references. So those two are very bad things. You've got to make sure you keep track of the heap allocated variables and that you free them when you're done with them. Can you mix and match types of scope and persistence? So let's suppose that I want to have a local variable in a function that has local scope but global persistence. This is why I use the static keyword. So static int count equals 0 says this is a variable whose scope is limited by the block in which it's declared, but its persistence is that of a global variable. Okay? Static local variables are not declared on the stack, they're declared in global memory. Okay? So static int count. Count has local scope, global persistence. And this is what you have to think about with a static keyword, is global persistence, local scope. When you apply static to a global variable, it's a similar thing, local scope, global persistence. The persistence argument doesn't make a whole lot of sense when you're applying static to a global variable because the global variable would have persisted globally anyway. But when you apply static to a global variable, you do limit its scope. Instead of limiting it to a function, you limit it to a file. Okay? So this is what you should have done on Lab 0 when I said you cannot create variables with global scope. Static int nFIFO is created. So this says create a variable at global scope called nFIFO is created, but since it's static, I want to limit its visibility to the file that I'm currently in. That way, even if some other file says extern int nFIFO is created, that symbol won't get exported, and the linker will say, I don't know what that variable is you're talking about. Okay. You can also apply static to functions. When you say that a function is declared as static, the same rules for global data variables apply. So what that means is a static global function has its scope limited to the current file only. So when you are tracing the printf source code, you're going to see some static variables and static functions. The scope of those guys, those symbols cannot be accessed except in the current file. Now, if you have a global pointer and you point it to a static variable and you allow other people to access the global pointer, you can access the static local variable by using a non-static global pointer. There will be an example of that in the printf lab. Okay, so just in summary, where is your variable? Your variable is on the stack, or it's in the heap, or it's in global memory. We have to deal with persistence issues. We have to deal with scoping issues. Okay, we'll continue to beat on this next time, and then we will barrel on into chapter 4. If you get stuck on the printf lab, I want to see you.
You still want to get together tomorrow after Jordan?
Yep.
Sounds good. I'll see if I can look at that stuff tonight or tomorrow morning.
Okay. Do you have either a laptop or a remote login to your machine that we can maybe, well?
I got my laptop.
Okay. Okay, laptop will be good.
We'll have to have an outlet. Battery at work.
Power out. I can do power outlet.
Sounds good.
Yep.